Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 33. So let's see, we've got this disc-shaped geometry supported by a pin with a spring attached right here like so. And somebody is asking for the natural vibration of the system. So imagine that this thing gets displaced from equilibrium a small amount. So imagine this point gets moved over to here. So then what we have here is we have an angle, theta. Now, the amount that the spring is stretched, right, is approximately equal to the arc length, which is this distance along this path. I say approximately. If you look at it, it's not exactly equal to that, but it's approximately equal to that. And that's equal to r times theta. So the potential energy within that spring, right? Now remember that potential energy for a spring is 1/2 k times distance squared. So the potential energy stored in that spring is now 1/2 k r theta squared. And that is the only potential energy in this problem. We don't need to worry about any gravitational potential energy or anything like that. Now, when this object is moving, picture this theta being a variable. It could also have a rotational kinetic energy of 1/2 I omega squared. Now the omega can be written, right, that's equal to theta dot. So the total energy at any given time is the sum of these two things. Write that out, take the time derivative of it, being very careful, and you should be able to get this written in the following form. Theta, you should end up with a theta double dot plus a number or something. I'll just put plus something times theta equals 0. And this something is going to have m's and r's in it. Oh, and the spring constant. Because the I, remember, is this is a disk, so you can use 1/2 mr squared. Okay. Once you get it to this point, remember the general solution for these looks like this. Theta is going to be a sine of b omega plus c cosine. Whoops, I meant omega t, and I meant that right here too. Sorry, I was thinking ahead. Okay. Now here's some good news. If all you're after is the frequency, the initial conditions do not matter. And what that means is you can just toss one of these. I would just throw away the cosine term. And as far as the frequency is concerned, that is the guy you're looking for right there. So take the second derivative of this thing, equals blah, 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 blah. That's going to go there. Then you take this, and that will go there. And you're solving for omega. It should look like omega equals the square root of a bunch of crap. And all this stuff should have m, r, and k in it. Okay? And then to get the period, omega times the period is equal to 2 pi. Because when this thing oscillates through one cycle, this is going to change by 2 pi radians. So that's how you get the period. And then the frequency is 1 over the period. So that's talked through. Hopefully that will get you through this problem. Have a great day.